Our derivative measures a rate of change. So that's something we know. If we think about the actual curve then, what does that mean? Well, the steeper the curve, the faster the change. So the bigger the number, it must be changing faster. Now, if my point is over here, P, what do I know? Well, I know that derivative is positive, right? Because the slope of the tangent. That's when we say it's increasing. It makes sense, the curve's going up. If it's right at the top, well, that's going to be horizontal. That's when we say the curve's stationary. It's not going up, it's not going down. And then, of course, once we slide down the other side, now the derivative is negative. We've got a negative tangent. Curve's going down, so we call it decreasing. If I've got 2 points on the curve, if I was to measure the slope of that secant, that would just be the average rate of change. Whereas if I just look at a particular point and find the exact slope of that tangent, that's the instantaneous rate of change. And often that's far more useful. Imagine you're driving a car or something like that, and police pull you over and say, sorry, you're going to book you for speeding. You can't turn around and say, oh no, sir, you're just looking at my instantaneous speed. If you were to look at my speed over the past hour, on average, I was only going this speed. That's not going to work. Instantaneous rate of change is a lot more interesting. Let's look at this question. So we have how appropriate with all the rain coming down. A water tank is being emptied. There's Q litres of water in our tank. The volume is given by Q equals 1020 minus T squared. So what's the rate of change of this? Well, we'll just have to differentiate. We've got a chain rule situation, bring down the power, lower the power, dip the inside, and we get minus 2000. It kind of makes sense that that derivative is negative because the volume would be decreasing. How much time does it take to empty the tank? Well, the tank will be empty when Q equals 0. So again, to justify what you're doing, make some sort of statement. This is why I'm doing it. Solving that equation, we get T equals 20. So we're all right, after 20 minutes. So when will water be flowing out at a rate of 20,000 litres per minute? So when is dq dt equal to minus 20,000 is what we're being asked. That rate of change. Solving that one, we get T equals 10. So after 10 minutes. But if they asked us what was the average rate it's flowing out during those first 5 minutes, well, we're going to need to find Q at both T equals 0 and also at T equals 5. Because we're going to find the slope of that secant. Rise over run, Q over T in this case. So there we have it. Minus 35,000 would be the slope of that secant. So that brings me to the equations of motion. One of the main reasons calculus was first thought about. And actually it was thought about by two different mathematicians. There's this argument about who really was the person who came up with it. Well, actually you'll notice I said discovered rather than invented, because of course you don't invent maths, you discover maths. It's all there. All the maths that we ever know and ever will know currently exists. It's just up to us to find it. We've got to find the math. So calculus was discovered, this fella, Gottfried Leibniz, or is it Leibniz? I always get that one wrong. A German, and it's actually his notations that we use for modern calculus. The other person, a lot more famous, Isaac Newton, of course, and he started using calculus to use the laws of motion, planetary motion, and things like that. Now, Newton's dot notation, we use that when we're talking about motion. We tend to use dot notation. Interestingly though, look at the ages when they came up with these ideas. So Newton was only 22, Leibniz was 28. He was a bit older when he came up with the idea. Displacement, velocity, acceleration. These are the three key things we talk about with motion. And often we just use x, because we like to look at straight line motion, and we think of the x-axis, we're just going along a straight line. And in physics we use s a lot of times for displacement. Displacement is distance, but with direction, of course. Now the negative sign and the positive sign have some meaning to it. It's basically telling you the direction in which you're going. Velocity we can symbolise in different ways, the most obvious one being v, of course, for velocity. But if I was to use Newton's notation, then it would be x with a dot. So x dot represents velocity, or the rate of change of displacement. Leibniz's notation is dx to t. That's the Leibniz notation. But essentially it's that. It's the rate of change of displacement with respect to time. So in other words, it's the speed of the object, but again with direction. The plus or minus has some meaning. And then we have acceleration. Lots of different ways we can write acceleration. A, again, being the most obvious. But it is the first derivative of velocity, so it could be v with a dot. It's also the second derivative of displacement, so x with two dots. dv to t, the derivative of velocity with respect to time, or the second derivative of displacement with respect to time. So all different ways we could write acceleration. And it's simply the rate of change of velocity with respect to time. Acceleration I always think is the unfortunate one, because we have displacement and distance. So distance is really just the magnitude. Displacement is then when we give it direction as well. And then we go to the next level, we have speed and we have velocity. Speed is just the magnitude, velocity is when we give it some direction. But then we get to the third one and we have acceleration and we have acceleration. We use the same term for both the magnitude and the one when we're saying which direction as well. I'm going to draw a couple of graphs here. I've got the displacement time. It's a travel graph if you think about it. Now I want to draw a velocity time graph and then also an acceleration time graph. But what do I know? I know that when the displacement graph is stationary, so up there, then velocity would be zero. So I'll mark it on the axis down there. And in fact there's another stationary point, so I'll plot that one in as well. I know that when the displacement graph is increasing, so for instance there, then velocity is positive. So I know on that graph I'll be in that section. And actually it's also increasing over on the right hand side as well. And of course when it's decreasing it'll be negative, so I know velocity is negative. I know I go in these sections here. The velocity graph is stationary there. How do I know that? That's when the graph above it inflects. So at that inflection point here, there must be a stationary point down here. And we get that shape. Now if you look at the original curve, whilst I don't have an equation, it certainly has the shape of a cubic. There's no surprises that when I differentiated it, I got something that's the shape of a parabola. What would happen with acceleration? Well, the same sort of ideas. I can say, well, hang on, that's stationary here, therefore it's at zero. It's increasing, so it's above. Over here it's decreasing, so it's below. I end up just with a straight line. And again, makes sense, because if I was going to differentiate a quadratic, I'd get a linear function. 9j is what we shall do today.